Okay, so in this example, we're told that blocks B and C are connected by a single and extensible cable, and that cable is wrapped around pulleys at D and E. In addition, the cable is wrapped around a pulley attached to block A as shown. We're asked to assume that the radii of the pulleys are small, and that blocks B and C move downward with prescribed speeds of VB and VC respectively. Given this information, we're asked to find the velocity of block A when SA is a given numerical value. Alright, so as in all these problems, we're going to try to utilize the rope length constraint idea here. And simply we're going to add up the length of each of these rope segments. And we'll assume, given that it's an extensible cable, that these add up to a constant. So if we do that, starting from left to right, we're going to first of all have a rope length segment of length SC. Then I have the hypotenuse of a triangle, which in this case is given by the square root of quantity 3 feet squared plus SA squared. If I move to the third segment there on the left, or excuse me, towards the right, we're going to have an additional length segment of length square root of 3 squared plus SA squared. And then finally there on the far right, I'll have a rope length of segment SB. And so I know if I add all this together, I'll recover a constant. We can go ahead and clean this up here a little bit and group things together. So if I do that, I'll have SC plus 2 times, in this case I'll write it as a fractional power, so 3 squared, let's just go ahead and write that as 9, plus SA squared to the 1/2 power plus SB is going to equal some constant that I'll just choose to call capital C. Now in this problem we don't want a relationship between SC and SB, but rather their velocities. And so what I'm going to do now is I'll take a time derivative of this expression. So if I take a time derivative of this expression, the first term will give me the speed VC, plus the next term is going to give me 1/2 times quantity 2 times quantity 9 plus SA squared to the minus 1/2 power. And I need to multiply it because it's a time derivative operation times the time derivative of what's inside those parentheses. So I'm going to have 2 SA times VA. And I'm going to add to that the time derivative of SB, which is simply VB. And I know that'll equal the time derivative of a constant, which will simply be 0. Now I can clean this up a little bit. You'll note right off the bat that the 2.5 cancel. And so what I'll end up with here now is VC plus 2 SA VA divided by the square root of 9 plus SA squared plus VB has to equal 0. In this case, if I look at that equation, I only really have one unknown, and that is VA, and so I can work to solve for that. And so if I do that, I'm going to get from here that VA is going to equal, in this case, minus VC minus VB divided by 2SA times, in this case, 9 plus SA squared to the 1/2 power. Now in this case, VA is going to be positive downward because SA is defined to be positive downward. And so if I want to write this in vector form, VA is going to be the minus of that in the J. And so this is going to give me VC plus VB times the square root of 9 plus SA squared divided by 2SA, all in the J direction. I think from here, all we need to do is plug in a few numerical values, so I'll leave that up to you to do. I feel very confident you can do it, so best of luck.